Hi future GISPs! I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to study the 210 websites, 1,155 book pages, 1,700 Quizlet flashcards, and 291 videos and podcasts included in the GISCI's recommended study material like I did when I passed the GISP exam. In this video, I'm going to teach you everything I learned about systems architecture and design. Systems architecture and design is the first section under the Systems Design and Management category of the GISP exam knowledge categories. Let's get started. System architecture. System architecture is the high-level blueprint of how a GIS system is organized. It defines the major components: servers, databases, networks, cloud platforms, file storage, desktops, and mobile devices, and explains how they all interact. Architecture determines the system's scalability, reliability, security, and ability to support enterprise-wide workflows. First, let's discuss the architecture design phases from the GISCI's official study guide. The GISCI's official study guide lists 4 architecture design phases: requirements phase, design phase, construction phase, and implementation phase. First is the requirements phase. The requirements phase identifies user needs, workflow demands, business goals, and both baseline and peak processing loads. This ensures the architecture supports the busiest moments the GIS will face, such as storm events, elections, emergencies, or public surges on web maps. Next is the design phase. The design phase defines the major architectural components: on-premises servers, cloud services, network topology, high-level database structure, security zones, and distributed GIS patterns. This is still conceptual, not detailed specs, so decisions focus on what the system should contain, rather than exactly what hardware to buy. Next is the construction phase. The construction phase includes acquiring hardware, configuring virtual machines, building databases, setting up file systems, and developing prototype applications. Lastly is the implementation phase. The implementation phase deploys the system to users, completes integration and operational testing, provides training, and establishes maintenance operations. These 4 phases together make up the architecture process, from concept to deployment. Now let's discuss enterprise architecture. Enterprise GIS integrates spatial data and workflows across an entire organization using shared servers, centralized data stores, web services, and governance. It reduces duplication, improves data consistency, ensures authoritative data sources, and supports editing and analysis across multiple departments. Enterprise GIS environments include database servers, storage area networks, virtual machines, terminal servers, web servers, map servers, desktop clients, mobile devices, and networks. These technologies are interconnected through local area networks, wide area networks, and internet communications. Now let's discuss distributed GIS architecture. Distributed GIS describes systems where processing, data storage, rendering, and user interfaces are spread across multiple machines or geographic locations. This enables modern GIS capabilities, such as Web GIS, Cloud GIS, Mobile GIS, and real-time sensor networks. Distributed GIS supports multi-office operations, remote field crews, cloud-hosted services, scalable web maps, real-time data feeds, and big data spatial analysis. OGC standards. OGC standards ensure that distributed GIS components communicate using standard formats for geospatial data and services. Mashups. A mashup is a web application that combines multiple distributed services. For example, a base map, weather data, and live traffic feeds. Now let's take a look at virtualization architecture. Virtualization creates virtual machines that run independently from physical hardware. Virtualization components include host machines, guest machines, hypervisors, and containers. A host machine. A host machine is a physical server. A guest machine. A guest machine is a virtual system running on top of a host. A hypervisor. A hypervisor manages and runs virtual machines. Containers. Containers are lightweight, isolated environments used for microservices or scalable geospatial compute tasks. Virtualization supports GIS by enabling server consolidation, faster disaster recovery, isolated map and DB services, cost-efficient scaling, and easier maintenance. Nearly all modern enterprise GIS environments rely on virtualization. Cloud architecture. Cloud GIS supports anywhere access, high-demand scalability, public-facing apps, collaboration with external partners, and hybrid deployments combining cloud and on-premises components. There are a few different types of GIS platforms. Types of GIS platforms include desktop, server, hosted, and enterprise. Desktop GIS. Desktop GIS supports local editing, map creation, and analysis. Server GIS. Server GIS provides organization-wide web services, shared datasets, and centralized processing. Hosted or Cloud GIS. Hosted GIS allows users to create and share content through platforms like ArcGIS Online. Enterprise GIS. Enterprise GIS integrates desktop, server, cloud, mobile, and web systems into one cohesive environment. Before we move on, it's important to clarify something that often confused me when preparing for the GISP exam. In traditional IT and software engineering, system architecture and system design are treated as two separate concepts. Architecture describes the high-level structure, the major components, how they interact, and the overall system blueprint. Design comes afterward and defines the detailed technical specifications needed to build that architecture. However, in the GISCI study guide, the term system design is listed as one of the phases of the architectural process. This reflects how the GIS field traditionally blends architectural planning with detailed design work under the umbrella of GIS system design, especially when implementing enterprise GIS environments. So even though the architecture and design are usually distinct concepts in the IT world, the GISCI framework merges them, meaning you must understand both as part of the overall concept of systems architecture and design for the GISP exam. Now let's explore some system design concepts. System design consists of detailed planning and specifications that follow architecture. System design converts the high-level architecture into detailed technical specifications for hardware, software versions, databases, networks, storage systems, performance expectations, and security. System design begins with identifying business needs. Identifying business needs consists of identifying who the users are, the tasks they perform, what information products they need, where they work, and what data and tools support their workflows. This ensures the system supports real organizational needs, not assumptions. The next step in the GIS system design process is a GIS needs assessment. A GIS needs assessment evaluates how GIS can improve workflows, reduce data silos, automate manual processes, and increase operational efficiency. A GIS needs assessment provides essential input for the detailed system design. After the business needs are documented, they must be translated into IT requirements. IT requirements include CPU, memory, storage, database schema, spatial indexes, network throughput, security roles and groups, firewall and authentication, and redundancy and failover. Capacity planning is also part of system design. Capacity planning identifies resource bottlenecks and ensures the system can support both average and peak loads. The Capacity Planning Tool. Esri's Capacity Planning Tool models user loads, service requests, network consumption, and hardware requirements. A workflow transaction. A transaction is a unit of work, such as a map request or a feature edit. Throughput. Throughput measures how many transactions the system can process per second or minute. A batch process. A batch process is an automated task that runs without user interaction, such as nightly ETL or raster processing. System design must account for both daily user workloads and after-hours batch loads. And now let's take a look at GIS software. The GIS software supports the architecture and platforms covered in this section, and includes desktop, server, cloud, mobile, and hybrid systems. Major GIS software packages include Esri. Esri is the most widely used commercial GIS platform, offering comprehensive tools for mapping, spatial analysis, data management, 3D visualization, geoprocessing, and enterprise web GIS. QGIS. QGIS is a free open source GIS used for mapping, data editing, spatial analysis, and plugin based customization across many operating systems and data formats. GeoMedia. GeoMedia is an enterprise GIS suite used for advanced analysis, data integration, and multi-user editing, especially within utilities, transportation, and government organizations. MapInfo. MapInfo is a desktop GIS commonly used for business mapping, market analysis, demographic studies, and site selection. GISCI. GISCI, now known as TerSat, is a GIS and remote sensing system focused on raster analysis, environmental modeling, and change detection. GISCI is widely used in academic and developing world contexts. Manifold. Manifold is a low-cost, high-performance GIS known for fast rendering, image processing, and extensible modules for spatial analysis. Maptitude. Maptitude is a GIS package designed for business analytics, providing tools for sales territory mapping, logistics, transportation planning, and demographic analysis. AutoCAD Map 3D. AutoCAD Map 3D integrates CAD drafting tools with GIS data, allowing engineers and surveyors to connect design drawings to spatial features and 3D environments. GRASS. GRASS is a free open-source GIS strong in raster processing, geospatial modeling, and scientific analysis. GRASS was originally developed by the U.S. Army Corps of Engineers. TNT MIPS, also known as microimages. TNT MIPS is an integrated GIS, CAD, and remote sensing system used for image analysis, terrain modeling, and cartographic production. AirDAS. AirDAS is a leading remote sensing and image analysis platform used for classification, feature extraction, photogrammetry, and raster data processing. Bentley Map. Bentley Map is an engineering-focused GIS used for infrastructure mapping, utility network design, and CAD to GIS integration within large enterprise environments. MicroStation. MicroStation is Bentley's advanced CAD platform used to create engineering drawings, infrastructure models, and GGN files that feed into GIS and design workflows. Small World. Small World is an enterprise GIS used by utility and telecommunications companies for large-scale network management, asset tracking, and infrastructure modeling. PostGIS. PostGIS is an open-source spatial extension for PostgreSQL that enables advanced spatial queries, geoprocessing, and geodatabase capabilities in server environments. These are the most well-known GIS platforms in use today. Understanding these platforms helps you evaluate architectural and design decisions for different organizational needs. Now you know everything I learned about systems architecture and design to easily pass the GISP exam. Don't forget to thumbs up and subscribe to my channel so I can keep helping people pass the GISP exam and build the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is a comprehensive, easily understandable, graphical, all-in-one resource for passing the exam. You can find the link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.